All right, now let's cover 3 practice problems at the end of the chapter. So 3 Doppler effect problems, problems 27, 29, and 31 at the end of chapter 22. Now one note, in the text, the information you're given on the speed of sound in air is for all of these problems. We're just going to assume that the speed of sound in air is 343 meters per second. So we'll just use that and just plug it into our Doppler effect equation. Okay, problem number 27. So there is a car horn which is sounding at a frequency of 560 hertz, and you're also given the information that the car is approaching a stationary listener and at a speed of 15 meters per second. So this will be a 2-part problem. The first part will be what is the frequency heard by the observer with the car approaching the observer. So that's the first part we'll do, and then we'll next calculate the frequency after the car has passed the observer and is moving away. Here's our general Doppler effect equation. The frequency heard by the observer is equal to the frequency being produced by the source. And again, we're going to assume that it's a constant frequency. The frequency is not changing. And times speed of sound in air plus the speed of the observer divided by speed of sound in air minus the speed of the source. So let's go ahead and plug in what we know. So the frequency heard by the observer, and also before you do this, you can already guess what a reasonable answer might be. So as the car is approaching, should the frequency heard by the observer be higher than the 560 hertz or lower? So it should be higher. Let's see how it turns out. So the frequency heard by the source is 560 hertz, frequency being produced by the source, and we'll multiply that by the speed of sound in air, 343, plus the speed of the observer. We're told that the observer is stationary, so that would be plus 0, divided by 343 minus the speed of the source. Now in terms of sign convention, then the speed of the source is going to be a positive 15 because it is an approaching situation. So this will be minus a positive 15. All of these speeds have units of meters per second. I've omitted them to save room on the board, but also they're all going to cancel out between the numerator and denominator anyway, and you're going to be left with hertz. So if you do your calculation, you're going to end up with 585.6 hertz, which is about what you would expect, because in an approaching situation, the observer will hear a frequency, an apparent frequency that's higher than the actual frequency being produced by the source. All right, next is part B. We only have to do a slight modification. So part B is what frequency is heard by the observer with now the car having passed and the car is now moving away. So in this situation, the car horn is still producing a frequency of 560 hertz. Speed of sound in air is unchanged. The only thing that's changed is now we have a moving away situation. So the speed of the source is now a minus, takes on a minus sign. So you can see how that changes our equation. The denominator now becomes 343 plus 15. And if you do the calculation, you now get 536.5 hertz frequency heard by the observer after the car is passed and is moving away, which is, again, what we would expect. Now let's take a look at the next problem, problem 29. very similar to number 27, just a few minor changes in the given information. Once again, speed of sound in air is given as 343 meters per second. So now we have a train that is moving at 20 meters per second, blowing its whistle at a frequency of 300 hertz, and approaching a stationary observer. And what are the frequencies heard by the observer as the train approaches and passes? Now you'll notice in the textbook you're given 3 answers. There's just the briefest of moments when the frequency heard by the observer might be 300 hertz, but let's just do the 2 situations, the approaching and the moving away. So part A, approaching So very similar to the last problem, where we have the frequency heard by the observer is equal to the frequency of the source, 300 hertz, times 343 speed of sound in air, plus the speed of the observer, which is 0, divided by 343 minus, again approaching, the speed of the source would be positive 20 in the approaching situation. So that is going to give you a frequency heard, an apparent frequency of 318.6 hertz, which is what you would expect. The observer will hear a higher frequency than what's actually being produced by the sound in the approaching situation. And then after the train is passed, we now have a moving away situation. And as before, the only thing that changes is now the speed of the source in the denominator has a negative value, and that will result in a frequency heard being less than 300. That now becomes 283.5 hertz. All right, here's our third problem, number 31. Only slightly more complicated than the last 2 problems. So in this case, you're given an ambulance that is sounding its siren with a frequency of 600 hertz, and the ambulance is moving north at 15 meters per second. So this little sketch here, sometimes a sketch helps to visualize what's going on. So you have an ambulance moving north with a sounding its siren at 600 hertz, moving at 15 meters per second. And there's a car moving south, and it's approaching the ambulance at 20 meters per second. So again, let's do part A, which is the approaching situation before the car and the ambulance pass. So the frequency heard by the observer would be the 600 hertz, and that would be times, again for this problem we were just given 343 meters per second as the speed of sound in air, plus the speed of the observer, and in this case we don't have a stationary observer, we have a moving observer, and that car is approaching the ambulance. That's at 20 meters per second, so that's plus a positive 20. And in the denominator we have 343 minus, and we also have a situation where the ambulance is approaching the observer at 15 meters a second. So that would be minus a positive 15 meters per second. So if you do the calculations, again, you would assume that the frequency heard by the observer will be greater than 600, and that ends up being 664 hertz. So if you get a result, in this case, for any of these problems, if you get a result in an approaching situation that is less than the frequency of the source, then you did something wrong in the calculation, and you can go back and check it. All right, and then part B, moving away. So moving away, then the speed of the observer now takes on a negative value, and the speed of the ambulance takes on a negative value because it's moving away as well. And this will cause the observed frequency to be much less than 600, turns out to be 541.3. Okay, so just a slightly different problem there. A couple of more comments in terms of other kinds of problems you might see. Now you'll notice we're not doing any conversions here, but it's possible that you might see problems that don't give you the speed in meters per second. You might be given the speed in feet per second. And if that's the case, if you're given the speed of sound in air with meters per second and the speed of the source and the observer in feet per second, you'll have to do some conversions to make sure the units are compatible. The other more difficult problem that you might see could be like this. You could have a problem where you're given every piece of information, let's say, except for the speed of the source. Let's say you're told what frequency is being heard by the observer, the frequency of the source, the speed of sound in air. Maybe you're told that the observer is stationary and what is the speed of the source of sound. So you can see that it's going to require some algebraic manipulation to get that equation into the right form for you to solve for that. And the other part of this is that you have to be careful and make sure you get the correct sign, because we know the sign convention as positive approaching, negative moving away. All right.